What if I told you this entire pattern started as a stack of flat plastic sheets? No casting, no mold, no magic, just engineering, precision machining, and a whole lot of planning. Today, we're taking you behind the scenes to show you exactly how a modern foundry pattern is made, from the digital 3D model to a finished production tool. Every pattern begins long before a machine ever starts cutting. It starts right here, on a computer screen. Meet Jordan. He's a mechanical engineer, a CAD designer, a CAM programmer, and a pattern maker. In many ways, he's the modern version of the master craftsman we talked about in our last episode. But what exactly do all those titles mean? And what do they actually involve? Before we can understand how a pattern is made, we first need to learn the language of pattern making. CAD. Computer-aided drafting, or also known as computer-aided design. Think of CAD as the digital blueprint. It's where every part begins. Every dimension, every radius, every hole, every feature. Before anything is ever manufactured, it first exists here as a complete three-dimensional model. Next, CAM. Computer-aided manufacturing. If CAD tells us what we're making, CAM tells the machine how to make it. It converts the 3D model into thousands of precise movements that the CNC machine follows to create the pattern. Draft. While the walls of this part may look perfectly vertical, they aren't. Draft is a very slight angle built into all patterns. Without it, the sand mold can't be removed cleanly from the pattern. Just a few degrees makes all the difference. Radius. Instead of sharp corners, we use smooth curves. They help the molten aluminum flow more easily, reduce stress concentrations, and help make both the pattern and the casting stronger. Shrink. When aluminum cools, it gets smaller, so every pattern has to start slightly larger than the finished casting. That tiny difference is called the shrink factor. It's almost impossible to see, but it's absolutely critical to producing castings that meet specification. Cavity. A cavity is an individual part location on the pattern that creates one casting. When sand is pressed against the pattern, each one of these sections creates a negative impression, or a cavity, in the sand. Once molten aluminum is poured into those spaces, each cavity becomes one finished casting. This pattern is a two-cavity pattern. That means every time we make one mold, we can produce two castings at once. Adding multiple cavities increases production efficiency, but also makes pattern design more complex. Every cavity has to match perfectly, every feature has to fill correctly, and every part has to meet the same dimensional requirements. Now that we understand the language, let's look at how a modern pattern actually begins. And just like the pattern makers of the past, the process starts with understanding the part. Before we create a pattern, we start with the finished component. This is the part the customer needs us to produce. At this stage, there is no pattern, no mold, no aluminum, just a digital model representing the final product. Every surface has a purpose. Every hole, every pocket, every radius, every mounting feature. All of these details have to be understood before a single piece of material is cut. This is where the pattern maker's role becomes important. He is not simply drawing a shape on a computer, he is translating a finished part into a manufacturing tool. He's asking questions like, how will this part separate from the sand mold? Where will the metal enter? Where will it flow? How will it cool? And how can we build a pattern that produces the part consistently thousands of times? But the finished casting model is only the beginning. Now we begin building the pattern. The individual part geometry is prepared, draft is added, machining allowances are considered, shrink factor is applied, and the features needed for the molding processes are incorporated into the design. Once one cavity is complete, the process can begin to scale. This single part becomes multiple cavities arranged on a pattern board. In this case, a 4-cavity pattern. 4 identical copies of the part integrated into one pattern board. But a pattern is more than just the shape of a part. The real skill is designing the entire system around it. The runners that carry the metal, the gates that control how it enters the casting, the risers that feed the metal as it cools, every feature has a purpose. By the time we finish this step, the pattern already exists. Not physically, but digitally. Every surface, every feature, every dimension. Now we know what to build, But how does a computer tell the machine to make it? Now the pattern exists digitally, but a CNC machine doesn't understand a 3D model. It doesn't know what to cut, how to cut it, or which tools will create the final shape. This is where we begin programming the pattern. The machine may do the cutting, but the decisions still come from the pattern maker. The first step is deciding how each surface will be manufactured. Different areas of the pattern require different approaches. Some surfaces need aggressive material removal, while others require light finishing passes to create a smooth, precise surface. We select the toolpaths, then determine which surfaces those toolpaths will control. Finally, we choose the cutting tools that will bring those surfaces to life. A finished pattern is not created with one tool, and it's not created with one operation. It's a combination of many carefully planned steps working together. Large cutters remove excess material quickly, smaller tools refine the shape, and finishing tools create the smooth surfaces and accuracy required for production tooling. Each operation builds on the one before it, until thousands of individual machine movements combine to create one finished pattern. But before the CNC machine ever starts cutting, we can test the entire process digitally. Software simulates every tool movement, every cut, and every pass. The result is a virtual version of the finished pattern before we ever touch a piece of material. It allows us to verify the process, catch potential issues, and make sure the machine will produce exactly what was designed. Once the pattern has been visually verified in a virtual world, the next step is translating that digital information into something the machine can understand. The CAM software takes all those carefully planned movements, every tool change, every cutting path, every movement and position, and converts them into a language called G-code. G-code is the instruction set that controls the CNC machine. It tells the machine exactly where to move, how fast to move, which tool to use, and when to perform each operation. This code is specific to the machine that will run it. The computer doesn't just send a picture of the pattern, it sends thousands of individual commands that transform the digital design into physical movement. At this point, the pattern has existed as an idea, a 3D model, a programmed toolpath, and a verified simulation. Now the final steps begin, turning those digital instructions into reality. Now the digital pattern is complete. The machine knows exactly what to do, but before we can start cutting, we need something to cut. This is where modern patterns at Thomas Machine and Foundry begin, a stack of large urethane sheets. These sheets come in a variety of sizes and thicknesses, from 1 inch all the way up to 6 inches thick. For most patterns, we use thinner 1 and 2 inch material, not because thicker material isn't available, but because using thinner sections allows us to be more efficient. It reduces wasted material, it makes the pieces easier to handle, and it gives us more flexibility when building large, complex patterns. The first step is cutting these large sheets down into manageable pieces. We start by taking the raw material and cutting each section to the exact size needed for the pattern blank. This process may look simple, but accuracy matters from the very beginning. Every piece needs to fit together correctly, because this blank becomes the foundation of the final pattern. Before any pieces are glued together, we create a glue-up plan from the 3D model. This drawing shows exactly how the pattern blank will be built, what pieces are needed, what size each piece should be, and where every section needs to be located. This is the bridge between the digital world and the physical one. The computer tells us what the final pattern needs to become, and the plan tells us how to build the raw block that it will be made from. Once the material is prepared, we begin laying out the glue-up. Every piece is marked, every location is identified, because once the glue is applied, there is no room for guessing. To keep everything aligned, a temporary hinge is created using tape. This allows us to position the loose piece exactly where it belongs, then rotate it into place once the glue is ready. The adhesive used for this process is a 2-part epoxy. It provides a strong bond, but also gives enough working time to carefully position each piece. Depending on the material and the conditions, the epoxy takes roughly 2 to 4 hours to fully cure. The glue is applied to the marked area, then the heat from a torch bursts any small air bubbles created during the mixing and spreading of the adhesive. These small details matter because the goal is to create one solid, stable block of material. With the epoxy ready, the loose section is carefully lowered into place. The tape acts like a hinge, keeping the piece aligned while we use the layout marks to position it precisely. Additional tape is added around the remaining edges. This keeps the epoxy contained and it prevents the piece from shifting while it cures. This process is repeated piece by piece until every section of the pattern blank is assembled. Then the entire process is repeated on the opposite side of the board. Layer by layer, piece by piece, the raw sheet becomes one large, solid pattern blank. It may not look impressive yet, but hidden inside this block is the finished pattern we designed on the computer. The next step is where everything comes together, turning this oversized block of urethane into a precision production tool. The pattern blank is complete, the design is finished, the material is ready. Now comes one of the most important steps in the entire process, telling the machine exactly where the pattern exists on its work table. Before the CNC can make a single cut, the pattern has to be positioned perfectly. It starts by placing the raw blank on these parallels. These are precision machined aluminum blocks. Their job is simple: make sure the pattern sits flat, parallel to the machine table, and perfectly level. It may seem like a small detail, but every cut the machine makes is based on this starting position. If the pattern is not positioned correctly here, every feature machined afterward will be wrong. Once the blank is sitting correctly, it's secured to the machine. The first job is alignment. We carefully dial in the leading edge of the pattern, then physically rotate the pattern until the leading edge is aligned with the machine. This establishes the pattern's position along the x-axis of the machine. In simple terms, we're telling the CNC exactly where this pattern starts. Next is finding the true location of the pattern on the machine. Using a specialty tool called an edge finder, we locate the outside edges of the raw pattern blank. Front, back, left, right. These measurements allow the machine to calculate the exact center of the pattern. Now we know where the pattern is located, but we still need to create reliable reference surfaces that will remain consistent throughout the entire machining process. The next step is creating these reference surfaces on the pattern itself. The front and rear edges are machined flat and precisely located. Then, the left and right edges are machined the same. These finished surfaces become permanent datums, or known starting points. They give us reliable reference points for future machining, inspection, or repairs. If a feature ever needs to be repaired or remachined, the pattern can be returned to the machine, aligned using these reference surfaces, and brought back to the exact same location. With these reference surfaces established, the mounting holes are machined into the pattern. These allow the pattern to be securely attached to the parallel blocks. The pattern is now locked into position. No movement, no shifting, just a solid connection between the pattern and the machine. With the pattern securely mounted, the parallels are reclamped onto the machine. Now the pattern is prepared for the final measurement. The top surface of the pattern is then machined flat. This creates the final Z reference plane for the pattern. From this surface, we can establish the exact height of the pattern in relation to the machine. Using a precision height block, we measure this reference surface to define the location of the cutting tools. This allows the CNC controls to understand the exact distance between the tools and the pattern surface. Every movement of the machine is now tied back to a known, repeatable reference. At this point, the machine understands exactly where the pattern is located. It knows the center of the pattern, the height of the pattern, and the relationship between every surface and the machine origin. The CNC doesn't just know that the pattern is sitting on the table, it knows precisely where that pattern exists in three-dimensional space. That accuracy is what allows us to create the complex geometry required for modern castings. With the pattern located, we load the cutting tools, load the machining program, and verify the final setup. Hours of planning have led to this moment. The digital model is ready, the machine is ready, the pattern blank is ready. Now it's time to make chips. And now, the moment we've been building toward, turning a digital pattern into a physical tool. What you're watching happen in just a few minutes actually took nearly 11 hours to complete. Every movement you see, every tool change, Every pass across the material was carefully planned back in the computer before the machine ever started. The process begins by removing large amounts of material quickly. The machine works its way through the block, slowly revealing the hidden shape inside. Then, as the pattern takes shape, the tools become smaller, the cuts become lighter, and the machine begins refining the details that make this a precision production pattern. Unlike cutting metal, this process requires no cutting fluid or coolant. The urethane material cuts cleanly and freely, allowing the machine to remove material without the need for traditional cooling methods. Instead, we use compressed air directed at the cutting area. This air clears chips away from the tool and helps manage heat created during the cutting process. This keeps the cutting tools working efficiently while keeping the process clean and controlled. Even though this process creates a large amount of material removal, the machine is designed to contain it. The CNC is fully enclosed and connected to a dedicated vacuum system that removes airborne particles and urethane dust. This keeps the surrounding work area cleaner and helps maintain a safer, more controlled manufacturing environment. But perhaps one of the biggest advantages of this process is that the machining can happen while we're away. These long machining operations are typically run overnight when the rest of the crew has already gone home. This reduces disruption from machine noise, maximizes the use of our equipment, and allows us to walk into the shop the next morning with a pattern that's near complete. This is where modern pattern making becomes incredibly powerful. A process that once required weeks or even months of hand craftsmanship can now move from a digital model to a finished production tool in a matter of days. But the technology is only part of the story. The machine can only do what the pattern maker has designed. The accuracy still comes from the planning, the knowledge, and the craftsmanship behind every decision. From a computer screen, to a block of urethane, to a finished pattern ready for the foundry, this is how a modern pattern is made at Thomas Machine and Foundry. We've now followed the journey of a pattern, from its history from handcrafted wooden tooling to a modern CNC machine production pattern. We've seen how an idea becomes a digital model, how that model becomes a tool, and how that tool becomes the foundation for thousands of castings. But there's a question that keen-eyed viewers may still be asking. If the pattern makes the outside shape, how do you make a part hollow? How do you create the passages, openings, and internal features hidden inside a solid piece of metal? How do you make something that has features you can see and features you can't? Because while the pattern creates the outside of a casting, the inside requires a completely different process. And that's where our next chapter begins. Next week, we'll explore one of the most important and often overlooked parts of the foundry process. We'll uncover how complex internal features are created, how the tools behind that process are made, and how those tools allow us to create castings that would otherwise be impossible. Join us next week as we continue to explore the hidden processes behind modern foundry manufacturing. And don't forget to like and subscribe if you enjoy this content to ensure you don't miss any part of this multi-part series.